We've been talking about Brayton cycles. Brayton cycles are the type of thermodynamic cycle found in natural gas power plants. We've found out that they're heat engines, so they have a thermal efficiency, and that they're a series of open system processes, so we can treat them mostly the same way that we treat Rankine cycles. The difference is the working fluid here is an ideal gas. So when it comes time for us to fix states to find things like delta H or delta S, we have to use strategies that are more similar to what we did in internal combustion engines than when we were dealing with water back and forth across a Rankine cycle. If I draw PV and TS diagrams for Brayton cycles, I can see that as I move from my inlet through my compressor, I'll typically assume that this is an isentropic process, at least at first. Then, as I add heat from state 2 to state 3, you can't tell on a TS diagram, but on a PV diagram, we can see that that heat addition happens at constant pressure. Then we go through a turbine, which can be isentropic, and then we can get an isentropic efficiency to find the outlet at the real turbine. Then we model this system by putting a heat exchanger between state 4 and state 1, even though we don't actually have a component here. Really, what happens is we exhaust this exit fluid from the turbine into the atmosphere, while at the same time pulling in air from the atmosphere at state 1. So that means we can sort of model this system as if there's another heat exchanger there, where that heat exchanger is the environment. We assume, because we're exiting into the atmosphere, so the pressure at state 4 is atmospheric pressure, and then we're pulling air in from the atmosphere, so the pressure at state 1 is atmospheric pressure as well. So we can model this heat rejection process as happening at constant pressure. Now, this is a cycle that consists of a series of open systems, and we treat this like a Rankine cycle, where we take each one of the systems and we make a series of assumptions. We'll say that there's steady state, one inlet, one outlet. We'll neglect kinetic energy changes and potential energies. Then we'll look at the individual components and we'll make a decision whether they're adiabatic or passive, or sometimes both if we're looking at a whole heat exchanger. And we'll neglect friction and heat losses between our different components. When we do that, if we can make these assumptions that we usually make, we'll find expressions for a compressor or turbine power, where it's m dot times h in minus h out, where the turbine power is positive and the compressor power is negative. We'll also find that heat transfer terms, like q dot in from the combustor, are m dot times h out minus h in. Here, we're adding heat in the combustor, so it's positive, and we're rejecting heat through the atmosphere, so that's negative. Then we're at the point where we have to ask, what's the fluid? Because now we have a symbolic solution and we're trying to find expressions for delta H. It turns out that it can be difficult to solve these states when we're talking about a cycle that uses ideal gases as a working fluid. My advice to you is always going to be look for the processes that are isentropic. Because if you have an isentropic process with an ideal gas, there are special equations you can use. If you're using variable specific heat analysis, then your ratio of pressures across your isentropic process, so this is typical for turbines and pumps where we're assuming they're ideal, then you know the ratio of the pressures is equal to the ratio of the reduced pressures. I can find these reduced pressures on table A22 in my textbook. If I'm using constant specific heat, I'm never going to find the individual specific enthalpies. Instead, I'll assume that the change in the enthalpy is equal to Cp times delta T, and I'll be left trying to find the temperature at the isentropic outlet. To do that, if I've assumed that specific heats are constant, then I'm going to look for an equation with K in the exponent, where I'm trying to find this ratio of temperatures, and I know the ratio of pressures, which is typical in these open systems. In a case like this, I see that temperatures are not delta temperatures here, so I know that I have to use absolute temperatures in either degrees Kelvin or degrees Rankine. Then we talked about how we can become master builders and put our Lego blocks together in a more complicated way to improve thermal efficiency. Right? Of course, they're not really Lego blocks, right? These are thermodynamic components. So one of the things we talked about was regeneration. Now, the nice thing about the Brayton cycle is when we do regeneration, we don't have to split the mass somewhere like we did in a Rankine cycle. Instead, we take this hot outlet fluid from the turbine and we pass it through the hot side of a heat exchanger while the cold side is getting air that comes out of my compressor and goes into my combustor. The nice thing about this is we're lowering our exhaust temperature, which has environmental benefits, but we're also saving some heat here. That means we're burning less natural gas. That's good for the environment, and it's good for the bottom line of our power plant. So when we use regeneration, we're, instead of going from state 2 all the way up to state 3 with this heat addition process, we only have to go from state X, which is the outlet on the cold side of our regenerator, up to state 3. So I'm saving some heat by preheating it with this exhaust fluid at state 4. I can talk about the efficiency of my regenerator by comparing the actual amount of heat that happens in my regenerator, that's going from state 2 to state X, with the maximum amount of heat, which would be going from state 2 all the way up to this same temperature where we are getting our exhaust gas from. So if those temperatures were the same, the specific enthalpies would be the same as well. So the maximum heat transfer we could get from a regenerator would be H4 minus H2. So if we compare that ratio, we get our efficiency of our regenerator. We can also use reheat in a Brayton cycle, just like we did in Rankine. When we do this, we take our turbine and we split it into 2 stages, a high pressure stage and a low pressure stage. And in between the two, we bring the fluid out of the turbine and we add more heat. When we do this, we get this extra area in our TS diagram. I usually call that a bleb. And that extra area means we get more power out of our system. And the rate of the increase of the power as we do this reheat is faster than the rate when we're increasing the heat rate in. So this increases our thermal efficiency. And the cool thing is, when we do reheat and regeneration at the same time, the reheat gives us a higher exhaust temperature, which means we can get more regeneration. So there's a synergistic effect of doing reheat and regeneration in the same cycle. That's what we're showing here, that when we do the reheat, we get this higher exit temperature or a higher exhaust temperature. And that means that our regenerator, if it was the same efficiency, would only come to here without reheat, but maybe would come all the way up to here with reheat. So there's this synergistic effect. The other thing that we're worried about with these Brayton cycles is that it takes a significant amount of power to increase the pressure when we're pulling air in from the environment. So one of the things we can do is we can split our compressor into 2 stages. So here we have the first stage, which is lower pressure, and the second stage, which is higher pressure. And what we do is we cool the fluid down in between those 2 stages. So remember, when we cool down a fluid, there's less Brownian motion, right? So it's easier for us to push those air molecules closer together. So what this means is that as we go from the pressure here at state 1 to the pressure after both compressor stages, we've actually put less power into the system. So we're increasing our net power by decreasing our compressor power. Hopefully that gives you a good overview of what a Brayton cycle looks like. But now we're going to move to a different kind of cycle that's at least partially different from a Brayton cycle. We'll see that these turbojet engines that we're going to talk about today have kind of a Brayton cycle at their heart, but then we add a diffuser at the inlet and a nozzle at the exit. So this is an interesting heat engine because our energy benefit of a turbojet turns out not to be net power. So this is the one heat engine we'll look at where the purpose is not to maximize the net power. But before we get into how turbojets work, I want to ask you a question. What is it that we need in order to fly? So it turns out, if I asked my kids this, they might tell me all I need to fly is faith, trust, and pixie dust. It's because they watch probably too many Disney movies and because they're not studying engineering yet. So because you're taking a class like this, you can move away from this sort of cartoonish version of the world, and we can start looking at what we actually need in order to get a big metal plane up in the air. So it turns out, when we have a wing, if it has the right profile, as it cuts through the air, we make a high pressure zone below the wing and a low pressure zone above the wing. What that means is that this pressure differential pushes the wing up. Now that force that pushes the wing up is called lift. So what a plane needs to fly is lift. How do we get lift? The important thing, a wing won't work if the plane's not moving, right? You've probably seen planes on a runway somewhere, right? Even if it's just in a movie, and it doesn't just spontaneously start to fly. Instead, we need the plane to be moving so that the wing starts to cut through the air, and only when the air is moving over the wing do we get this lift force. So, what we need to develop for the plane to get lift is thrust. So we need the plane to have some kind of an engine on it that's pushing the plane forward. We call that a thrust force. Now, when the plane pushes forward, the wing starts to cut through the air, and that makes this high pressure below the wing and a low pressure above the wing, and that gives us this seemingly miraculous lift force, right? This force that lets us put something as big and heavy as an airplane up in the air. So we can do this in a couple of ways, right? But the engine that we are going to study here is called a turbojet engine. So not a propeller type engine, which might be called a turboprop engine, but in this case, a turbojet engine. So how does a turbojet engine work? That's what we're going to try to look at today. But we can come back to our previous question and answer now, what do we need to fly? So it turns out my kids were close to right, because it's always nice to have faith in the pilot, and the rest of the flight crew and the maintenance people, right? And the engineers who designed the plane. A little pixie dust probably doesn't hurt, right? But the important thing from an engineering standpoint is the thrust, because it's the thrust that ends up giving the lift. So in order to fly, we need faith, thrust, and pixie dust. So what is thrust? Thrust is a force. We can get the thrust force by looking at the change in momentum over time. Momentum, I believe you've taken this, right? So maybe you have to sort of jog your memory a little bit, but momentum is going to be mass times velocity, right? So if I want my thrust force, I can look at the momentum times the velocity at the outlet of my engine minus the momentum times the velocity at the inlet of my engine, and divide that by some delta t, and I would get a thrust, right? So this is going to be a force, right? But here, I don't really have a delta t, but I have a mass divided by a delta t, which is like a mass flow rate. So if I take the mass flow rate at the exit times the velocity at the exit, minus the mass flow rate at the inlet times the velocity at the inlet, then I'll get my thrust force. If I have a system where there's one inlet and one outlet, and we're at steady state, then both of these mass flow rates are the same, and my thrust force becomes m dot times the velocity at 2 minus the velocity at 1. So I said at the beginning here that the turbojet engine is a little bit unique in terms of the heat engines we look at, because it's not trying to develop net power in the way that we've been thinking about it. So it's not trying to get as much power as we can get spinning on this shaft, right? Typically, in like a Brayton cycle or in a Rankine cycle, we'd want as much power spinning that shaft so that we could connect it to an electrical generator and put power out on the grid, right? But an airplane's not connected to the grid, right? It's flying through the air. So we have a different desired energy effect here. We want some thrust, but we don't want a force here. We want thrust power, right? Because this is still going to be some kind of power divided by the energy cost, which is still going to be a heat rate in. So how do I get thrust power? So thrust power, the units, if I'm talking about metric, should be in something like kilowatts. So that's kilojoules per second, which is kilonewtons times meters per second. But I know already an equation that gives me the thrust force in something like kilonewtons. So I need to multiply that by something that has units of meters per second. What has units of meters per second? Velocity or speed. So I can take my thrust force and multiply it by the velocity of the jet, and I can get a thrust power. So my thrust power is going to be my thrust force multiplied by the velocity of the jet, or m dot times v out minus v in multiplied by the velocity of the jet. The desired energy cost, I've already told you this, and probably it's not a surprise. So we need some kind of jet fuel in our jet, right? So we need to burn that fuel to generate heat, because this is a heat engine. It's just we're turning this heat energy into this thrust power, right? So our energy cost is still going to be heat in. So our thermal efficiency is still going to be some sort of power divided by some heat transfer rate in. But the kind of power we're interested in is this thrust power instead of the mechanical power that we're usually interested in. So if I wanted to get a thermal efficiency for a turbojet engine, this is the equation that I would use. Now, the textbook doesn't actually talk about thermal efficiency of turbojet engines, and we won't test this on an exam. But I still, because we've been talking about the characterization for all these other cycles, I still wanted to give you some idea of what the efficiency is that we'll talk about in these turbojet engines. So one of the tricky things when we're dealing with these turbojet problems is that we'll often be using a moving frame of reference, right? So when we're talking about these turbojets, it's kind of like we're a crazy person that's standing out on the wing of the jet as it's moving. So even though the air might be still, it feels like it's whipping into our face because we're standing on top of this plane wing, right? Probably not the safest place to be, but that's our moving frame of reference. So we might have to shift our frame of reference as we're trying to calculate things like velocities in problems like this. So what does a turbojet engine look like? The cool thing about this is that we already know what the turbojet looks like in the heart of the system because it's basically a Brayton cycle. We have some air that's coming into a compressor, increase the pressure, then we go through this combustor to increase the temperature and the enthalpy. Then we go out of this turbine, which generates some mechanical power. We already know how to use analysis to solve a cycle like that, right? So again, we got to remember that the turbojet engine is a little bit different. And what makes it a little bit different is that first, we're on an airplane wing flying through the sky, right? Standing on the airplane wing, right? So we sort of have this idea that we're moving at the same velocity as the jet. So we're in this moving frame of reference. But then we also added diffuser before our compressor because it feels like there's some velocity coming in here, right? Because the velocity is whipping in our face. We're standing on the wing, right? And we want to take that kinetic energy of the fluid and turn it into enthalpy. The component that does that is a diffuser. And then at the end of the turbine, we want to take all or as much of the enthalpy as we can over here and turn it into kinetic energy. Because remember, that thrust power that we're trying to develop here comes from the fact that the velocity is shooting out the nozzle very fast, right? So we want this to be a very fast flow that's coming out the back of our nozzle, right? And we want to maximize the velocity coming out here, right? So you may be getting the idea that kinetic energy is going to be important in this cycle, and that's definitely true for at least part of the cycle. So kinetic energy is important anytime we're not in the Brayton cycle part of the turbojet. It's important in the diffuser, particularly on the port of the diffuser that doesn't touch the Brayton cycle. So kinetic energy is going to be important coming in, and in the nozzle at the port that's not touching the Brayton cycle. So the kinetic energy here is going to be important at the outlet of the nozzle. So again, we have to remember that we're this crazy person standing on the wing of the plane, right? So even if the air is still, it feels like the air is coming at us, right? So we want to analyze this problem, at least when we're doing the analysis, from a moving frame of reference, so that it feels like there's some velocity of fluid coming into the diffuser, even though if we were in a stationary frame of reference, if there wasn't any kind of headwind or tailwind. So the purpose of this whole system is to maximize the thrust. We want this outlet velocity to be as fast as we can make it so that we can get lots of thrust here. So kinetic energy is important at the inlet to the diffuser and at the outlet of the nozzle. In the center of our system is going to be this Brayton cycle. But it's a very special Brayton cycle because what we want to do is maximize the velocity here. What that means is we want as much enthalpy in the fluid as we can when it comes out of the turbine, because we want to turn that enthalpy into kinetic energy at the exit of the nozzle. And the way that we do that, the way that we preserve as much enthalpy as we can coming out of the turbine, is that we only run the turbine in the Brayton cycle here so that it can run the compressor. We're only trying to break even in terms of power in the Brayton cycle because real purpose of this cycle is to maximize the kinetic energy at the exit of the nozzle. And if we got any extra mechanical power out of here, that's some power that we can't turn into kinetic energy. So one of the things that people consistently do incorrectly on these Brayton cycle problems is they forget that the backwork ratio of the Brayton cycle is equal to 1. What that means is that the compressor power is equal in magnitude to the turbine power. Now we know that if we use the first law, these things are going to have different signs because the turbine power is positive and the compressor power is negative. But we want the magnitudes to be the same. Another way of saying this is that the backwork ratio in the cycle is equal to 1. Now, you may have noticed that I said that multiple times. I used to have professors that would tell us, hey, the student's job is to figure out what 10% of the things that the professor says are important, right? What's going to make it on the test? And one of the ways that you can figure out what the professor thinks is important is it's the things that they say multiple times. I'll say it again. The backwork ratio of the turbojet engine, at least the Brayton cycle part, is only 1. The compressor power is equal in magnitude to the turbine power. So how do we solve this problem? If you guessed we'll use the first law on every component, then you're correct, right? This is thermodynamics class. That means we do the first law of thermodynamics as often as we can. If you don't know what to do, try using the first law. So we're going to go component by component, and I'll show you what the solution of the first law looks like for each one of these components. So the purpose of the diffuser is to take as much of the kinetic energy as we can coming into the diffuser and turn that into enthalpy at state 1. Notice how the textbook denotes these different state points. It talks about the inlet of the diffuser as state A, and the outlet of the diffuser, which ends up being the inlet to the compressor, as state 1. I think that's because they want to preserve the same state numbers as we go through the Brayton cycle so that the inlet to the compressor is still state 1. Right? So the purpose of the diffuser is to maximize the enthalpy going into the compressor. So how do I do first law on a diffuser? Right? You may not remember this because the last time we talked about this was when we first introduced open systems. So we'll assume that the diffuser is operating at steady state, that it's got one inlet and one outlet, that the potential energy change can be neglected, that it's both adiabatic and passive, so it's well insulated and doesn't have any fan blades like a turbine. But now, usually for most components, we would also say something like the kinetic energy change can also be neglected. But we can't do that in this case because the whole purpose of this component is to change the kinetic energy at the inlet into enthalpy at the outlet. So the thing that we do here is we say that the states that touch the Brayton cycle all have 0 kinetic energy. So what we're saying is that in this diffuser, we can take all of the kinetic energy from the inlet and turn it into enthalpy at the outlet. So what we do is we assume that the velocity at the exit of the diffuser, that's the part that's touching the Brayton cycle, is equal to 0. Now, if all that is true, then we can find H1, and H1 will be equal to HA plus VA squared over 2. At least that's the equation we'll get if we're dealing with metric units. If we happen to be dealing in imperial units, this equation will change, right? Remember, anytime this kinetic energy term sticks around, the hair on the back of our necks should stand up, or maybe, I guess, we should feel a disturbance in the force, right? Because we know that the units here are going to be difficult to deal with. If our velocity is in meters per second, we'll divide this by 2,000 to get kilojoules per kilogram, right? But I leave this as VA squared over 2 just to get us to the right quantity, and then I'll trust you when you're doing problems to use the right conversion factor, because it'll be different if I talk about meters per second or if I talk about kilometers per hour. If I talk about imperial units, I have to divide by 2gc in the kinetic energy term just to get to the right quantity. But if my velocity here is in feet per second, this will give me foot-pounds per pound mass. But h, if I looked it up on table A22, would be in BTU per pound mass. So I'd have to take this and divide by 778 just to get to BTU per pound mass. So imperial units are always trickier, but the kinetic energy term is tricky no matter what. So remember, when you're dealing with diffusers and later nozzles, it's going to be important for you to remember to track your units. So that's how we deal with the diffuser. The next thing we have to do is deal with the Brayton cycle. The good news is we mostly know how to do this, right? There's only this extra wrinkle that what we're trying to do in this Brayton cycle is not maximize the turbine power or the net power. Instead, we're trying to maximize the enthalpy at the outlet of the turbine. So we're trying to only run the turbine so that we can run the compressor. The backwork ratio here is 1. For all of these components that are involved in my Brayton cycle, they'll all be steady state. They're all one inlet and one outlet. There's no change in kinetic energy. I'm assuming that's 0 everywhere inside my Brayton cycle. No change in potential energy. My systems here, the compressor, the combustor, and the turbine, are either going to be adiabatic, that's the compressor and the turbine, or passive, that's the combustor. I'll also neglect any kind of friction or heat losses in between all my components inside my Brayton cycle. When I do that, I'll get the equations that I'm used to seeing for turbines and compressors, that m dot times h in minus h out is equal to power. And I know that my turbine power is going to be positive and my compressor power is going to be negative. My combustor will have a positive heat transfer rate because it's heat in, and that will be m dot times h3 minus h2, or h out minus h in. Again, I might not be given enough information to solve all the states here. So I'll have to use this extra piece of information that the backwork ratio here is equal to 1, or that the turbine power and the compressor power have the same magnitude. So if my backwork ratio is 1, what that means is that m dot times h1 minus h2 is equal to negative m dot times h3 minus h4. Notice that I dropped the subscripts on the mass flow rates here because I'm assuming we're at steady state with one inlet and one outlet in all of these components. If that's true, then I can divide both sides by m dot, and I'll get that h1 minus h2 is equal to h4 minus h3. So if there was one of these states that I couldn't fix, like say h4, then the way that I fix it is by using the fact that the backwork ratio here is 1. So I'm almost done here. The only thing I need to do is look at the nozzle. Remember, the nozzle, again, kinetic energy is going to be important here, but only at the outlet. I'm going to assume that the kinetic energy at the port of the nozzle that touches my Brayton cycle, that's state 4, that the kinetic energy there is really not that important. It's fairly small. So the assumptions I'll make for the nozzle is that it's at steady state, that it's one inlet, one outlet, that changes in potential energy can be neglected, that it's adiabatic and passive, and that the velocity at the inlet of my nozzle is equal to 0. In this case, now I'll get that the velocity at the exit squared, which is often what I'm trying to solve for, divided by 2, is equal to the h at the inlet of my nozzle minus h at the exit of my nozzle. At least that's what I do if it's a metric problem. But what do I do if I'm dealing with imperial units? Here, I need to divide this kinetic energy term by V exit squared divided by 2gc. So this term changes just so I can get the right quantity. But again, for both metric and imperial, this now gives me the right quantity, but the units will probably be off. If my metric velocity is in meters per second, I'll divide by 2,000 and not 2. And if my imperial velocity is in feet per second, then here I'm going to have to divide by 778 to go from foot-pounds per pound mass to BTU per pound mass. But if I can do all that, then I will have fixed all of the states for my turbojet engine. And if I can make all the assumptions that I've talked about, here's a list of what the different states look like, or what the first law looks like for each one of these individual components. Right? For the diffuser, we know that it's the kinetic energy at the inlet that we're changing into, that we're putting into this specific enthalpy at the outlet. Compressor and turbine powers are what we normally expect them to be, but the backwork ratio is equal to 1. The combustor is treated the same way as a combustor would be treated in any Brayton cycle, m dot times h out minus h in. And for my nozzle, I'm trying to turn this change in enthalpy into kinetic energy. So I'm trying to maximize that velocity at the exit. So this is good, and this is pretty much how commercial airplanes work, right? Although, in order to get the math right, and I'd like to be flying on commercial airplanes where engineers have got the math right, we want to get the units correct here, right? So anytime this kinetic energy term sticks around, we got to remember to look at the units. That's true in metric, and it's true in imperial. The imperial equations, remember, will look a little bit different because we got to divide those kinetic energy terms by GC just to get the right quantities. And then we still have to deal with units after that. So the nozzle and the diffuser are going to be tricky. Remember to stop and think. So our turbojet characterization looks a little bit different than the characterization we use for other heat engines because our energy benefit here is thrust power. Even if we don't end up using this equation in this class, it's important to remember that the thrust is what we're trying to maximize. So it's the velocity at the exit of the jet that's the interesting part. So for certain aerospace applications, we sometimes want to be able to go faster, right? So if you're dealing with military aircraft, you need to be able to, in some instances, add more velocity to your aircraft. And we can do that, right? The way that we need to do that. So how do we get velocity, right? Velocity, what we do is we turn enthalpy at the inlet of the nozzle into kinetic energy at the outlet of the nozzle. So what we can do to add more enthalpy at the inlet of the nozzle is after the exit of the turbine, we can add what we call an afterburner. The afterburner does just what you might think, in that we burn more fuel here to add more heat. It's a little bit like a reheat cycle inside a normal Brayton cycle or inside a Rankine cycle. We burn more fuel so that we can add more energy into the system. That increases the enthalpy going into the nozzle, and then that gives us more kinetic energy at the exit of the nozzle. If I was drawing a TS diagram in this case, what I do is I'm going through my diffuser, which I'll say is isentropic. Then I'll go through my compressor. If it's isentropic, this will be a vertical line too. Now I'll add heat through the combustor. Then I'll go through the turbine, developing enough power only to run my combustor. Then I'm going to do a second combustion phase in my afterburner to increase the enthalpy at state 5 going into the nozzle. Then I turn as much of this enthalpy as I can into kinetic energy and maximize the velocity at state 6. So this isn't something that you're going to see on a commercial airline, because commercial airlines are more interested in fuel efficiency, because saving even a little bit of fuel for a commercial airline when we're running planes consistently, basically from here to all points in the world, will mean big environmental and financial savings for the companies that are running those airplanes. But in military applications, it's more important to preserve the well-being of the pilots. So what we need to do sometimes is add this extra step, right? So it's better to burn more fuel and keep the pilot of the plane safe. So that's what we do with an afterburner. So hopefully this gives you some idea of how we can run these turbojet cycles. I'll see you next time when we'll go through a full-blown example of a turbojet engine.